what do you have to do in order to get to Sacramento? So if you're at Lake Tahoe and you're going over Highway 80, you have to put in some energy to get up to a little bit higher peak, Donner Summit, and then you can turn the engine off and just coast all the way down to Sacramento. And you can't actually do that, but in some parts of it, you could just turn your engine off and coast. So the reason you don't just roll downhill to Sacramento is that in order to get rolling, you have to put a little bit of energy in to get over an energy hill. And the same holds true for reactants. So if you think about sucrose, if there's no energy at all around sucrose, no energy whatsoever, what are the odds that bond is just going to break apart?
Very low.
It's very, very low, right? So what supplies the energy to break the bond? It pushes it up to a little bit of a higher energy state so it can fall down into glucose and fructose. What is that energy that's required? Where does it come from?
The enzyme.
Not the enzyme, but
Environment.
water. So as long as there's water moving around, right? We look back here. As long as water, ignore the sucrase. Just imagine sucrose floating around. As long as everybody is moving quickly, if the water bumps into it in just the right way, the bond could break. So you always have to invest a little bit of energy to get the bond to start breaking and complete the reaction. All that enzymes do is they simply lower the amount of energy required. And by lowering the amount of energy, they just increase the odds at any given moment that one of those things will break. That's all they do. It's like, no, I just have so many like analogies that I want to use. It's so hard. Okay, so endergonic and exergonic. How do you guys feel about that? So what do you think the reaction is? Let's say you want to build up a protein from amino acids. Is that going to be energy requiring reaction or an energy releasing reaction? Energy requiring, right? If you want to build up starch from glucose, is that an energy requiring reaction? Most absolutely, all right? So just generally for us, if you think about polymers being built, those are endergonic reactions. Polymers being busted apart are going to be exergonic reactions. You know, I mean, there's some, it's a little bit more complicated than that, obviously, but as a general rule, things that go from simple to complex are endergonic, complex to simple are exergonic. Okay. So, in order to get us ready to discuss the article, I want to talk with you guys about what's called a biochemical pathway. So, thus far, we've talked about chemical reactions, endergonic, exergonic. We say that an enzyme can bind to the reactant and encourage a reaction that spontaneously would occur to happen faster. But when you think about a biological system and you think about all of the complicated reactions they have to do, there's never going to be one enzyme that can just do everything. So what happens in a biological system is you often have this series of reactions that, like assembly line fashion, do one reaction to a substrate, release a product that becomes a reactant for another enzyme, which releases a product, which becomes a reactant for the next enzyme in the sequence. And I want to introduce this idea of a biochemical pathway in the context of an enzyme inhibitor. Right? So a biochemical pathway is just a series of enzyme catalyzed, which remember just means sped up, reactions. So in order to illustrate this, I want to use this molecule. Anybody know what this one is? Looks like a poodle.
Oh, fat.
What's that?
Is it fat?
Nope. It will make you gain weight. Sort of a carbohydrate. It's alcohol. So this is ethanol. And when you drink ethanol, so we're going to illustrate a biochemical pathway in the breakdown of ethanol. All right? So you've got ethanol, and that's going to be our first reactant in the pathway. You introduce it into the pathway because you drink a beer, or a shot of vodka, or whatever you do. So, unlike a car, like an internal combustion engine, that you can literally just put a certain amount of ethanol into it and ignite it, and it will drive the car, we don't have a single step reaction. We have to do a whole bunch of steps in order to break down ethanol. So, the first thing we do is we take that ethanol, and the first enzyme in the pathway, I'll call it enzyme number 1, takes ethanol and it converts it into this molecule. And it's called alcohol dehydrogenase, which I bet some of you have heard of. Any nods of agreement? I just try to think of enzymes that you might have heard of just in the popular press. And alcohol dehydrogenase, I really can't think of many others you might have heard of. So ethanol, it's an alcohol. It gets converted into this through an enzyme, alcohol dehydrogenase. This molecule here, one name for it is acetaldehyde. And this is not it. This isn't the final part of the breakdown pathway. We still need to convert it into something else before it fits in to a whole bunch of other enzyme catalyzed reactions that your body can do. So what we do is we take it and we convert, so we're going, remember, you don't have to memorize these structures. I just want to show you that they really are just molecules having little tweaks to them. Remove a hydrogen, all right, alcohol dehydrogenase. And then we convert that into this molecule here, which I like to know is the, or referred to as the poodle with handwarmers. Right? And anybody know what this is? Who's taking chemistry?